All right, we're doing lecture like this today because it's crashed 3 times so far when I try to write on it. All right. All right, so some quick strategy. So I wrote a lot of text here, so you can just copy it down onto like a note card or something afterwards. So don't try and copy it all right now. I just want to talk you through it. So as you are well aware by now, in thermo, the hardest thing is getting confused at which equation to use because there are many ones and they all sort of involve the same variables. So here are some general outlines. I think I gave most of these at the beginning of the practice test as well. Don't worry if you haven't done the practice test yet. This will be still applicable. So some key words to look out for that'll sort of, when you see the word, you'll be able to snap to at least like, or at most, 2 to 3 equations that might be relevant. So that'll greatly help you. Some key words, obviously, isothermal, isobaric, and isochoric are some immediate hot button words. They immediately tell you, let's use isothermal as an example. In the case of an isothermal process, as soon as you see that in the question, you know a couple things are simplified and are probably going to be your toolbox. The first one is that for isobaric processes, Boyle's law applies. Okay, so that's one equation in your toolbox. The next thing is that the first law in all these cases simplifies in some way. This is also true for adiabatic processes. In this case, you should write out the first law every time. And identify what variable is either 0 or in a simpler form. In the case of an isothermal process, delta T is 0, so delta E thermal is 0. So your first law is just Q in equals negative work in. So you can use that to answer a question. Additionally, the work done during the process, it is either immediately told to you, for example, isochoric means 0 work done, or it is told to you indirectly through the first law. In the case of an isothermal process, you might be told the heat and asked the work. Or you can use the other equation for isothermal. I think it's like nRT log of Vf over V initial. So I have all these listed on the equation sheet under like the work done section. I tell you for isothermal, isobaric, isochoric. And then what does the first law look like for isothermal, isobaric, isochoric processes? So all these simplifications are listed out. But this process sort of tells you which 2 equations should you try and jump to. Either the Charles-Boyle's law ones or the simplified first law. That's a great place to start, and it'll solve probably 90% of questions. For adiabatic processes, they're kind of like the cousins of these 3. So instead of using Boyle's law, PV, it's now P final, V final to the gamma power. Or, well, initial or final can go on either side. Sorry. So this is the analog of Boyle's law. And then, just like in the case of isothermal baric or choric, the first law simplifies. Because adiabatic, the definition of adiabatic is that Q equals 0. So the first law is now delta E thermal equals work in. So if you ever see a question that's like, a process is adiabatic and the temperature change is this much, that's telling you indirectly what number this is. What's the work done? It's a trivial problem. The non-triviality comes in realizing you have to use this equation. But as you can see, there's sort of a guidebook hinting which equation you should use. Okay, another thing is that whenever a gas is told to you to be monatomic or diatomic, sometimes they'll tell you like oxygen gas, and it's just, you know it's diatomic. I'll tell you on every problem. You know CV is either 3/2 R or 5/2 R, and gamma in that PV to the gamma equation, it's either what, 5/3 or 7/5 or something like that. So you actually know those values if the question ever tells you a gas is diatomic or monoatomic, even though the question doesn't list them explicitly. And again, don't feel the need to write all these out. I will put these up and you can copy them onto your cheat sheet index card. Okay, second page of strategy is if the question ever involves the word like find the ratio of volume before the compression and after the compression, you should try, if you can't get it immediately, dividing a copy of the relevant equation by itself. Pretty much this is always the ideal gas law, and that's actually how you derive Boyle's law, so if you just use Boyle's law, that's cool too. Also, in some rare cases where there's a before and an after, there's a problem on the practice test where you actually divide this equation by itself, the 3/2 kT by itself. So it's very useful if you're told the ratio of the initial and final temperatures, and you're asked about, in terms of the initial energy, how big is the final energy? Okay, I've mentioned this one a bunch here. Whenever heat is mentioned, especially if the question is asking about one of the other two variables in the first law, you should certainly be writing out the first law. If you don't, you're kind of throwing. The only thing I'll say is that sometimes heat appears in calorimetry problems, and those are sort of first law problems where you just write out all the Q's and they total up to 0. But in general, when you have a heat problem that is with like an ideal gas, let's say, you're going to want to write out the first law. Okay, for thermal energy changes, just remember that there are two similar concepts. There's delta E thermal, right, the change in thermal energy, compared with this other formula, which is only useful for one problem. The E is like 3/2 or 5/2 kT. And I'm just going to put this 3 in dash because it could be a 5. The right one is useful for the absolute amount of energy a gas has at a certain temperature. And the left one is useful for changes in thermal energy. The left one is infinitely, infinitely more useful. Okay, if you see the words freezes or melts, or you see ice put into something in calorimetry, or it tells you the water boils when you put hot metal in, that's a signal to, in addition to your normal MC delta T plus MC delta T terms in calorimetry, if there's something freezing or boiling, you're going to want to add in the latent heat terms, which are L times whatever mass of object is changing phase. And again, it could be a plus or a minus. I tell you which to use on the equation sheet, depending on if it's a melt, boil, freeze, condense. Okay, and then lastly, if you see a question asking about an engine, you should be drawing the engine diagram. And that basically contains the conservation of energy equation in it graphically. Okay. I have some big amounts of text on these next slides. Again, these are for you to read through after. They're for reference. You see this is a literal wall of text. This is for if you ever get stuck in corners and you are panicking and have no idea what to do. There's a couple good emergency ripcords to pull. I've already talked about all of them through the class. The first one, for example, is try the ideal gas law on the beginning and end of the process to figure out the fourth variable if you know 3 of P, V, N, and T. If you aren't given 3 of them, maybe it's a Boyle's law type problem. Try that on the beginning versus end, either Boyle's or Charles, depending on what kind of process it is. The second one is just saying use the first law if it says heat, in case you forgot it from the strategy slides. Another good one, and I'll put a star on this one, is that when people write out the first law, they often freeze up and forget that they can replace delta E thermal with NCV delta T. That's always a good first step. It's sort of like if you have a kinetic energy problem in physics 1 and you refuse to replace KE with 1/2 mv squared, you're probably not going to go anywhere. This is like a good first step. What should you replace in the first law? Okay, the next case is already covered. This one that I'm circling right now, that's already covered in the strategy. So is this one. If the gas is mono or diatomic, you know CV. Okay, this one in blue is if you are in a calorimetry problem and let's say you have ice and it melts, the temperature of the water immediately after the ice has melted is 0 Celsius. It comes out of the ice at 0 Celsius, at the freezing point, and then continues to heat up. So sometimes you will forget that on a calorimetry problem. The second to last slide is again just saying try taking a ratio of the relevant equations if you were asked about the before and after of a process. And the last one, I actually used my one blank on the slide for something that I think everyone already understands. If you don't draw the engine diagram, that is a play that's for suckers. So don't do that, draw the engine diagram. Again, copy these down from the slides afterwards onto your equation sheets. Okay, some common mistakes I expect to see. Absolute temperatures must be in kelvins. This includes the ideal gas law, the Carnot engine efficiency formula, the E is 3/2 kT formula. Those all involve just the variable T, the absolute temperature, compared with equations that involve delta T's, such as MC delta T. There you can use Kelvin or Celsius. But for these equations, I think you're used to it in the ideal gas law, but it's especially tempting to forget about it during the Carnot engine problems. So just make sure you're using kelvins. If you aren't getting an answer for one of these problems and you can't figure out why, worth checking this out. Remember to convert to pascals, but I think you guys know that already. It's very easy to accidentally put T final for T initial and T initial for T final in MC delta T. Remember, delta T is T final minus T initial, like every other delta. Right, delta V is V final minus V initial, the same thing for T. So just be sure that T final and T initial are the right places. Another common mistake is people mix up adiabatic and isothermal. Adiabatic means heat input is 0. That doesn't mean that temperature change is 0. It just means that temperature change comes from work, according to the first law. That is different than an isothermal process, which is that the temperature is held fixed. Okay? In that case, the work and heat inflow or outflow offset each other to keep the temperature even. Okay, number 5, there's a piston problem on the practice exam. These, even though they don't look like it, they're isobaric processes between the initial and final. The reason is that the piston needs to support, the gas needs to support a certain amount of weight beforehand. Then you cool it, and it's going to compress until its pressure is strong enough again to support what's on top of it. Okay, so piston problems, you should try applying the isobaric equation, which is Charles' law. Another common mistake is people go crazy with PV to the gamma. The only equation that involves gamma is P initial, V initial to the gamma is P final, V final to the gamma. The ideal gas law is still the ideal gas law. There's no gamma in the ideal gas law ever. Okay, the only time you use gamma is in the equivalent of Boyle's law for an adiabatic process. Number 7, since you haven't done much practice with it, I find myself particularly susceptible to this. In the PV to the gamma equation, you're taking volume to like the 7/5 power. It's very common for people to write volume to the 7th divided by 5, and your calculator doesn't understand that this is to the 7/5 power. It takes volume to the 7th and then divides by 5. So just be sure that you are grouping the parentheses in the right place, right? It should be V to the parentheses 7/5. Again, I just say that because we haven't done a lot of problems and it might snare someone. So just double check if you aren't getting the right answer. And the last common mistake is applying the Carnot efficiency, that's like the ideal perfect efficiency, to any non-Carnot engine. That formula for the Carnot efficiency is essentially useless, except for you might be told the efficiency of your engine is half of the perfect efficiency using those temperatures. So in that case, you calculate the perfect efficiency using this one use of this equation, and then take that number, divide it by 2 to get the efficiency of your actual engine. Okay, you cannot apply this to anything except a perfect engine, and besides this one scenario which I wrote here, it's essentially useless. Okay, so I'm going to start going over some problems now. When I get to the numerical plugging in step, I'm not going to write out the numbers because there's a couple I want to go over, and also I was stalled 10 minutes by my stupid computer. So I list here what problem in the practice test each of these is. So that way when you're going through, you can always look back to these. All right, again, don't try and copy down these problems if you haven't. Just try and read them, understand what they're asking so you can understand what I'm saying, because I'm going to need to move on pretty fast. So in this problem, we have, and I actually think this is one of the hardest problems despite being the second question, and I honestly choke my explanation in the solutions video. I stumble for like a minute and a half trying to figure out what's going on. So in this problem, you have a bucket of water at 0 Celsius, and you put some ice in. And the ice is cooled well below 0. And you're asked what happens to the system as it approaches equilibrium. Now, intuitively, you have two objects of different temperatures, so they're going to try and exchange heat in order to get to the same final temperature. That way, no heat will flow anymore. So what's going to happen is that you can sort of view it as like coldness is being given off by the ice, but technically heat is being given off by the water to the ice to try. Well, I guess it's not to try and warm it up, because what actually happens is, I'm going to explain it in the intuitive way, actually. The ice is very, very cold, and the water is already at its freezing point. So as the ice and water talk to each other thermally, the ice is giving up some of its extra coldness to the water, and it's going to convert some water into ice. At the cost of that energy, the ice is going to lose some of its temperature, or it's going to get a little hotter. So what's actually happening is heat is being taken from the water and being inputted to the ice. But as you take any heat from the water, it has no more temperature left to give. So as it gives off heat, it freezes. Okay. So kind of a clunky problem. The water gives heat to the ice, and at the cost of giving up that heat is no more temperature it can lose. It freezes, and then the ice increases in temperature slowly towards 0, but more and more ice is forming from the water. So what happens is that a little more ice forms, and the water stays at 0 Celsius, and eventually you end up with ice and water at 0 Celsius. Okay, again, if you didn't have time to copy this down, you'll have to either go back and look at the video or look at the slides. Okay, this problem is a lot of text. Basically, it's telling you start with, let's say, water at 200 Celsius, so well above the boiling point, and you're cooling it all the way until it's -5 Celsius, below its freezing point, and asking for how much heat is required for that process. So basically, you'll see in the solutions video, I just draw like a giant temperature scale here. So let's say the substance's boiling point is here. So it's a gas up here. It's a liquid in between, and then here is the freezing point down here, and it's a solid. You take a substance from an initial temperature here down to a final temperature here. So while it is still a gas, you should use mCv delta T, and you have to use C for the gas phase. Depending on if the substance is a gas, liquid, or solid at the moment, it's going to have a slightly different specific heat. That's what these three numbers are right here. Okay, so use mCv delta T for the gas phase. Sorry, I'm writing extremely small. That superscript says gas. Then it condenses. Okay, so you have to use latent heat. to get the energy required to convert from a gas to a liquid. Then it cools down in the liquid phase, now that it's a liquid. Then it freezes. There's another latent heat term, the heat of fusion, because it goes through a phase change. And then finally, as you dip below 0, or whatever it is in this problem, for ice it would be as you go below 0 Celsius, you have the final heat required to change its temperature even further. And I believe each of these latent heats is negative because it is going to the lower energy state. So it requires negative heat. It gives off heat as it gets cooler. And then you just plug in all the numbers and you get the answer. Okay, but this sort of organizational strategy on the right is pretty helpful. Again, you're just adding up a bunch of different heats from cooling off, freezing, or sorry, cooling off, condensing, cooling off more, freezing, cooling off more. Okay, here's like where the real, not the real questions, but the strategy is going to start to be really important for these questions. So this one you can write down if you want. This is a very good one. It's a qualitative question, which, like a conceptual question, which makes it hard because there's no numbers. And it also has a lot of those keywords. I don't know why I say the temperature in Kelvin. It's just, does temperature go up or down? I'm going to emphasize that it is compressed, not expanded. Okay, so some possible things we might want to do. Let's first highlight the key words here. Okay, obviously the one that jumps out, probably because I spelled it wrong, so it's underlined in red, is isobarically. That is an immediate keyword, so it tells you you're instantly restricted to 2 or 3 equations to solve the problem. So the first law might be applicable, but I don't say anything about heat. I see temperature, but remember, that's not heat. Temperature is delta E thermal. So I could try the first law. I don't know if I'd get anywhere. I'm going to try Charles' law, okay, because it says isobaric. So my 2 options are try the first law, try Charles' law, see if I get anywhere. Okay, Charles' law is VF over TF equals VI, or sorry, yeah, VI over TI. And this sort of has what I need. It talks about a compression, so I know the final volume is less than the initial volume. And I'm asked what happens to the temperature. So I'm going to rearrange this equation to have temperature final over temperature initial equals V final over V initial. Okay, and this is getting somewhere. VF is less than VI because it's compressed. So this number is going to be less than 1. I don't know, it's like 0.3. Some random ass number. Okay, what this tells me is T final is 0.3 of T initial. So the gas cooled down. So the temperature decreased. An equivalent way you could have gotten here is, I think, yeah, you could have used the ideal gas law itself. If you hold P constant and N and R are obviously constants, if you decrease this number, or sorry, if you decrease volume by compressing it, in response, T has to go down as well because the ideal gas law still needs to be true. So that's another equivalent way. Or you could have taken 2 copies of the ideal gas law and divided them by themselves, in which case you would have re-derived this formula right here. Okay. But in any case, the key word was that the process was isobaric, which told us you should try these 2 equations first. And if you go through the practice test, you'll see pretty much every problem is actually secretly just one of these, or it's calorimetry or engines. But every ideal gas problem is pretty much one of these. Okay, this one is a question that's out in left field. So this is that one weird question where I talk about the absolute thermal energy of a particle. So if you ever see average thermokinetic energy, I mean, it's that one equation, right? So it's E is whatever the number of degrees of freedom over 2 times the Boltzmann constant times the absolute temperature. Okay, so not immediately clear exactly what I want to do. There's a couple ways you can do it. You could substitute in the temperature and find the expression for what K is, and then try plugging it in later for a new temperature. Or you can take 2 copies of the equation and divide it by itself. Okay, this is particularly hinted to you by the fact that it's a before and an after, and you're asked the final energy as like a multiple of the initial energy. Okay, that's a big hint. It's hard to see, but it is a hint. You're asked what multiple of the initial energy, K, is the final energy. So let's try dividing the equations. Okay, I have 1 copy for the final energy and final temperature, and 1 copy for the initial energy and the initial temperature. And we're going to divide them. Okay, number of degrees of freedom is a property of the molecule, so that cancels out. And then the 2 and the Boltzmann constant cancel out. So what I get is that the final energy over the initial energy is T final over T initial. T final is 150 plus 273. And T initial is 50 plus 273. Remember, I have to work in Kelvin. And if you plug in numbers, this turns out to 1.3. So the final energy is 1.3 times the initial energy. Okay, and again, the main idea here is the hint that told you to use these equations in the first place was this average thermokinetic energy. Only place where this equation is useful. And then how I knew to divide one by the other was I was asked what is the energy in terms of a multiple of the initial energy. So I'm looking for a ratio. Again, if you haven't done these problems yet, you could be like, oh, I wouldn't have figured that out. Don't worry, most people wouldn't figure it out immediately. Okay, here is the infamous piston problem. Now you know from your emergency strategy or whatever slide I put it on, piston problems where you cool it down, they're isobaric processes because the gas needs to hold up the weight before, and then it's going to get compressed after it gets cooled until it has enough pressure to hold up the weight again. For isobaric processes, Charles' law applies. Oops. Okay, piston hints it's isobaric. Okay, I know T final and T initial, and I'm asked about the ratio of the final height of the piston to the initial height. Okay, the volume of a cylindrical piston, I suppose I didn't write it was a cylinder, but it could be anything. It's pi r squared times the initial, or the final height, or the initial height. The radius of the piston doesn't change, so the pi r squareds cancel out. So I get that height final over height initial is whatever T final divided by T initial was. Now, again, it's not delta T, so I have to use kelvins. So T final is 107 plus 273, and T initial is 27 plus 273. And if you plug this in, what do you get? 1.26. Okay, again, the two main hints in this problem were the piston problem immediately is an isobaric problem. And you were asked about the ratio, so Charles' law is an obvious place to look for ratios. Equivalently, you could do the ideal gas law divided by itself, and you would get the exact same equation. That's what Charles' law is. Okay, here is a full strength problem. I think this is the hardest problem on the practice test. Okay, I just want to highlight some keywords and outline the strategy. This is a monoatomic gas. Okay, so we know CV immediately. CV equals 3/2. Okay, we have an isobaric process, which tells us we should either try using Charles' law or the first law, simplified. And the last buzzword is we are asked about the heat input. So this tells me I should immediately use what equation? The first law, right? Yeah, it's on all counts, this is pointing first law in many, many aspects. So the first law, as usual, in its like pure form, is this. Okay, for an isobaric, now I should try and simplify this, right? Like, remember how I said if you just leave kinetic energy without replacing it with 1/2 mv squared, you go nowhere? You should actually replace delta E thermal with what it's equal to. So delta E thermal is always equal to N capital CV delta T. Okay, that one you should pretty much always do because that's always true. And then what work is replaced with, it might be nRT ln V final over V initial, or it might be minus P delta V, or it might be 0. You got to replace it with whichever one it's equal to for the given process. For an isobaric process, work is minus P delta V, because P is constant. You don't need to do the integration. Okay, so I'm going to rewrite the first law. And again, I haven't done anything terribly complicated yet. Okay, I'm going to write Q in red for a reason I'll explain. Okay, so here's our equation. I'll let you guys copy for a second. Okay, this is another important general strategy to take with you for future classes. So I know I've harped this all semester long. If you have one equation, you can handle one unknown. If you have two equations, you can handle two unknowns. Okay. In this case, the unknown you actually need to find to answer the problem is Q in. So this is an actual unknown that you aren't going to be able to find in another way. So every other number in this equation had better be findable, at least. You had better be able to find it in some way. So let's check what we have. Okay, we have, let's see, we have CV, so CV is good. We have pressure, and we have the V final and V initial. So those variables are all good. So we have two problem childs that we need to deal with. We don't know the number of moles of gas. And T, remember, T is T final minus T initial. We are told T initial, so this is good. But so we don't know T final, so that's an issue. The instant we get both these numbers, the problem is done. So we have an actual unknown in red, and we need to deal with these unknowns in blue. We need to figure out what they are through other methods, and then we can actually find the unknown we actually want. So we're kind of on a head hunt for N and T final. Okay, it isn't told to us directly in the problem, so first emergency step, because we start panicking, is let's try the ideal gas law. All right, I know the temperature, pressure, and volume at the beginning, so can I find N? Perfect. So using the ideal gas law, I know I actually do know N. I'll have to do a tiny bit of work, but I'll know it. Okay, T final. I start panicking. I don't really know what it is. Well, I have two options. Let me try the first one again. Let me try using the ideal gas law at the end. Do I know the pressure at the end? Yes, it's isobarically expanded at 3 atmospheres. Do I know the volume at the end? Yes. Do I know N at the end? Yes. I just found that for my last headhunting adventure. So I actually do know T final as well. It's going to take a little bit of annoying ideal gas law, but I know it. And at this point, you can plug all your numbers in and you get the actual number Q in as your answer. Okay, so this process of an unknown that you actually are not going to be able to find, and then your laundry list, your hit list of variables that you need to find out in order to finish the equation, this is like a systematic way you can go through the problem. Okay, and as far as gas law problems go, first law problems, this is literally as hard as it could possibly get. So if you can do this, you can do pretty much anything. Okay, I'm not going to go over this one because I did it as an in-class. Just remember, if ice melts, you need the LFM in there. And you need to assign the sign manually, depending on if it melts or boils. All the MC delta T's, they automatically come with the correct sign. So you just do MC delta T for one object plus MC delta T for the other object equals 0. But then you need to add in the latent heats because there's melting. I'm also not going to go over this one because it was an in-class. Well, most of these were, but this one is one we did recently. This one, I just want to identify the strategy. You're talking about an adiabatic process here, and you are told diatomic, so you know what gamma is. So PV to the gamma is an obvious approach option. Okay, so PV to the gamma is an immediate. Is like an immediate hint. And for temperature, you can use TV to the gamma minus 1 that's on the equation sheet for adiabatic processes, or you can use the ideal gas law once you know the final volume. And just something to point out, I don't think I tell you the initial volume. So if we use our newfound headhunting analogy, V final is the variable you actually need to figure out. You are told P final is 4 atmospheres and P initial, but you don't know V initial, so you need to deal with this guy, otherwise you can't finish the problem. How might you get V initial? Well, let's try what's worked every time. Let's try the ideal gas law and see if we have enough. We have N, T, and P, so we can definitely find V at the beginning. Okay, here we have another in-class problem from our final class. This is the typical problem involving the ideal engine. Okay, so your engine is not ideal. The actual engine in the problem is not ideal. Yes, it's tragic. But it's told to you that its efficiency is 60% of what the ideal engine's efficiency would have been. So you want to calculate the ideal efficiency. I believe this is the equation. Someone check me. I think this is it. You're going to compute what eta ideal is. Okay, maybe you get, what do we get out for this problem? All right, yeah, you get out 0.653 when you plug in the temperatures in Kelvin. That's what a perfect engine would have been, but your engine is not perfect because you are not perfect. Your engine is 60% of that as its efficiency. So your engine has eta equals 0.392 instead from taking 60% of that number. And this tells you what work over Q hot is. Okay, so then you just draw your diagram. It tells you, or actually you don't even need to, work out. Actually, no, I would be a sucker if I don't do that. Work out is 1,000. Q hot, we don't know, but we know work out in this equation, so we can take 1,000, divide it by 0.392 to get Q hot. And then if we needed it to, we could get Q cold, but the problem actually was nice and didn't ask about that. But we could get it in principle. Okay, so this gives us the answer for Q hot is this, from taking 1,000 divided by 0.392. Okay, a graphical heat engine question. I think we agreed we're not going to put a full heat engine on there because it just takes too long. Something I want to remind you is that when you're determining what heats are Q hot, what heats are Q cold, any heat going into the gas counts towards Q hot. So in this problem, 300 joules are going from the hot reservoir into the gas itself. So Q hot is 300, and then the system exhausts 150 of heat outputted to the cold reservoir. Again, you just get those from totaling up all the things, all the heats that are leaving the gas. You don't total up all of them at once to get some total heat. You split them up based on whether they are coming in or coming out. Okay, and then obviously this tells you the work, which gives you the efficiency. Right, work would be 150. Okay, I threw in some cheeky choose the correct explanations. So in the video, I go over this one in great detail. I just want to outline the reasoning. It's kind of surprising, and this is why this isn't a question. Sorry, this is why this is a question. I want you to remember it forever. Delta E thermal equals mCV delta T is always true. It's not only true for constant volume processes. The equation Q equals mCV delta T is actually not always true. You were taught that in chemistry because you were dealing with solids or liquids which didn't expand. For those specific objects, work in the first law, right? Work would normally be here, Q plus W. Work is 0. So you're allowed to make that swap in your chemistry classes, but not here. And again, the video goes over the other two. Okay, and I'm not going to go over this one because we're essentially out of time. You just want to write out the first law, and this question is immediately solved. Again, the hint is it's adiabatic. All right, so everyone please come to class Wednesday. So we're going to do a class picture. I want to have you sign some things. So anyone on the Echo, please come to class. If you don't normally come to class, I guess don't, but everyone else please do. That would be awesome. So I'll see you guys on Wednesday, and I'll have office hours this week.